Guess I'll wait a couple minutes or more people get here. Yeah, pull up the here. All right, here people come. Participants thing up too. All right, well, there's not very many of you here compared to how many people are enrolled today, but you know, you guys are enough. I'm happy to talk to you. Let me move this down so I can see you. Okay, cool. How's it going? Did you get your homework in on time? Just barely, like right under the wire? Yeah, all right, that's cool. All right, so does anyone have any questions or anything they want to find out about? No, all right. All right, so last time at the very end of class, we were talking about this theorem, which says that if you have a set A, and if you have a bunch of permutations, if you consider the collection of all the permutations of A, the set of permutations forms a group. So, and where the operation is function composition. And then I asked you to move into breakout rooms and talk about this. And I think many of you made progress in this. Would it help for me to write some of this down, or do you feel like you understand it all already? Like, I don't want to bore anyone with stuff that you already figured out yesterday. What do you think?
I think it would be helpful to go through it.
Go through it together? Okay, let's do that. So thanks, Mia. So let's see, here's a proof. So we're going to assume hypotheses, right? So let A be and not be set. And let SA be collection of all permutations. Let me write it this way. So it's all the sigmas, such as sigma is a permutation of A. Want to show SA's group. Well, SA with function composition is a group. Okay, so there's either 3 or 4 things to show. We know that we need to show closure, inverses, identity, associativity, but function composition is always associative. So I'm just going to state that, and you can state that yourselves whenever we come onto this. So maybe I'll start with that. So we know function composition is always associative. So it remains to show closure, identity, inverses. This is really some slang, but I think you know what I mean by these. So I'm going to just stick with that slang. What is a permutation? We should probably know what that is. Someone remind me what the definition of a permutation is?
It's a function that maps the elements of an A back to other elements in A.
Yeah, that's right. And it's got some special properties.
Both one-to-one and onto.
Yeah, thanks, Connor. So yeah, one-to-one and onto. So if you think that would be helpful, we could sort of add that in. let me move this over. How am I gonna do this? I can add this in here. So this is the set. These are all the maps from A to A such that sigma is 1-to-1 and onto. Okay, so closure, we need to choose two elements in SA, show that their composition is in SA. So choose arbitrary sigma and tau in SA. We want to show that sigma composed with tau is in SA. If you're going to show something like this, the reason that I did this orange step in the first place is if you're going to show something like this, you need to have a crystal clear idea of what the objects are that you're dealing with. You know, if you're not totally comfortable with the definition of permutation, then you're going to have a really hard time showing that something's a permutation. So that's why I wanted to make sure everybody was on the same page with that. If I want to show the composition is in SA, what I have to do is show the composition as a map from A to A and is 1-to-1 and is onto. Those are the conditions to be in there. Okay, so let's do that. So since sigma and tau are in SA, we know that they both map from A to A, and sigma and tau are both 1-to-1 and onto. So let's see, what does sigma tau do? Sigma follows tau. Well, it starts at A and then it goes to A and then it ends at A. I don't really know how you want to show that unless you wanted to say something like, you could say, you know, A, and then sigma takes it to A. Oops, sorry, tau goes first. And then tau takes it to A, and then sigma takes it to A. And then, oh, look, the composition went from A to A. And then we just have to show that they're 1-to-1 and onto. Why is the composition 1-to-1? Where have we seen that before? That's actually one of your quiz problems. Do you remember this first quiz you ever had? I don't remember if you guys had 1-to-1 or onto, but one of the groups had 1-to-1 and the other group had onto. Okay, so we proved in an earlier quiz that a composition of 1-to-1 functions is 1-to-1 and a composition of onto functions is onto. Okay, so there's not really anything to say. Therefore, the composition is both. So it's a member of S of A. There's not a whole lot to say for this part. But does anyone want to ask questions about whether you feel like I said too much or not enough? Or Okay, you can also ask in the chat if you have questions, but you feel shy about saying something out loud. And you can even send it private secret chat just to me, and so then no one will even know that you said anything. All right, that's closure. What about identity? I heard some people talking about what they thought the identity element was. Can somebody tell me what they think the identity element would be like?
Would it be a function that just maps the element back to itself?
Yeah, that's right. It's going to just map whatever element it is back to itself. So that when the point is that when you pose it with something, you should not affect it at all, right? So if you take the input and you put out as output the same as your input, you're just sort of passing it through. You're not doing anything. So that's exactly what the identity is. And let's call it I guess. So define I from A to A by I of little a equals A for every little a in the set. Claim this is the identity. Of SA. And how do you show that? Well, we have to show that, composition with some other element doesn't change it. Okay, so to do this, choose an arbitrary sigma in SA. We want to show that I follows sigma is just sigma, and also sigma follows I is also just sigma. Here's where it might you might find yourself stuck. How do you show that two functions are the same? I want everybody to type something in the chat of how they think they need to do that. Yeah, this today is going to be an incredibly hard day compared to the others. So I'd really like to hear, not this part, but the part we're going to get to. So I'd really like to start hearing your feedback because, I understand it. I can just blow through it. And but I really want to hear where to be pausing. Okay, good. Got some input. Show that every output of one is the same as the other. Yes, exactly. So there's actually a couple things to do. One of them is show you have the same domain, but that's small and that's obvious here. And then the other thing is exactly what, what Connor and Tanner are saying. Great, thank you so much. Which is that it does the same, it gives the same output for the same inputs. So what you want to do is show that, so first show that they have the same domain. And for all x in the domain, f1 of x is the same thing as f2 of x. Maybe you're just being quiet because you understand everything and I'm going too slow. That happens. You can never tell. Okay, so this is what we're going to do here, right? We're just going to, so they have the same domain. Everybody's domain is A. You can pose it up with other things whose domain's A and range is A. Okay, so both these functions have domains A. We don't really care about that. But let's figure out about the second part. So choose an arbitrary x in the domain. Then I composed with sigma of x. Well, composition of functions that's just I of sigma of x. So that means put sigma of x into the function I. What does I do? It just takes the input and passes it through to be the same as the output. So that's just sigma of x. And that's what we wanted. Also, the other way, sigma of I of x, that's sigma applied to I of x. And I of x doesn't do anything. It just takes x and sends it to x. Okay, so both of these functions are the same. So I follows sigma equals sigma, and sigma follows I is also sigma. What about this last one, inverses? We can start it, choose an arbitrary sigma in S of A. We want to find an inverse. We want to show sigma as an inverse in S of A. How do I know what are the conditions for sigma to have an inverse function?
The permutation has to be a bijection.
Yeah, it has to be a bijection, exactly. Any function, in fact, if you a function has an inverse if it's a bijection. You need one-to-one so that going backwards, you have a well-defined function. You need onto so that going backwards, everybody in the domain of the inverse has some place to go. So you need both of those pieces. And we have that because we've got permutation. So excellent. So so we want to show it has an inverse in A, but since sigma is already a permutation, we know it is a one-to-one and onto. We know it's a bijection. And therefore it has an inverse. Have we shown what we need to show? No, we haven't, right? We haven't because we still need to show that this inverse is an SA, right? Maybe that's got an inverse, but it's not in the supposed group, so it's not going to help us at all. So we need to show sigma inverse is in S of A. Well, go back to see what it means to be in S of A. Where are we? Here. Has to be a map from A to A, and it has to be one-to-one and onto. Okay, that's okay. So since sigma maps from A to A, we know that sigma inverse maps the other way, which is from A to A. What about sigma inverse? Is sigma inverse one-to-one? What if it wasn't 1-to-1? What would be wrong with sigma? Anybody know?
If sigma inverse wasn't 1-to-1, then sigma wouldn't be onto, so sigma wouldn't be a bijection.
Oh, so close, so close. If sigma inverse wasn't 1-to-1, then maybe it was like 2-to-1 or something, like there'd be two things going to one. That would mean that going forward, the sigma would have one thing going to two, and that would violate the definition of being a function. But you're right, it violates something about sigma. Okay, so note sigma inverse is 1-to-1 for, if it wasn't, sigma would not be a function. You might think in terms of the vertical line test, so it wouldn't pass vertical line test, for example. Also, sigma inverse is onto. Why sigma inverse onto? Well, it just takes, sigma inverse just takes everybody, sigma pushed them forward, sigma inverse just pushes them right back. So if there was somebody that sigma inverse missed, that would mean there was somebody that if there's somebody that sigma inverse did not hit, oh, you guys are looking this way, somebody that sigma inverse did not hit, that would mean that there was something of sigma that didn't get applied, that sigma didn't apply to it. It'd be something over here that didn't manage to go anywhere with sigma. Maybe you were going to divide by 0 or something like that. But sigma being a function means it uses its whole domain, means that sigma inverse is onto. Because sigma is a function, so it uses its whole domain. Okay, so cool. So thus sigma inverse is an element of SA, and we have a loop. Right. Actually, whenever you're permuting things around, if you have just let's say we're only talking about finite sets. If you're permuting finitely many things around, it doesn't really matter what the things are. It doesn't matter if you're shuffling 3 pencils or if you're shuffling 3 coins or if they're 3 numbers. It doesn't matter, right? The number of ways to shuffle them is going to be the same. The number of permutations the same. The ways to shuffle them are the same. And so we sort of default to saying that we're just shuffling the first n numbers. So instead of writing S sub A, we usually write S sub n, or we're doing the first n numbers. So I guess this is the notation / definition. I don't know which one you want to call it. Thanks. Okay. If you let A be a finite set, which is 1 to up to n. Then the group of all permutations on A instead of calling it S sub A, which is what we called it in the previous problem, S sub A doesn't really point to how many elements are in A. We just call it S sub n. Is called the symmetric group on n letters, and is denoted S sub n. when I learned this, I thought that was super awkward. Like, why did we call this symmetric group on n letters when really we had n numbers, right? We had 1, 2, 3, 4, 5, dot, 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 up to n. We had n numbers. And why are they calling it letters? And I don't know for sure the answer to this, but I've made up a reason for myself that I feel comfortable with. And here's what I think the reason is. Because we don't care that those are numbers. We're not going to add 1 and 2 together. Think about their existence as a number and what the number means. We're just going to treat them as symbols that we're moving around with names that we're familiar with. So we're sort of thinking them, so letters meaning symbols rather than numbers, meaning the symbol has a mathematical meaning to it. Okay, so that I think that's why they call it that. In any case, that's what we call it. All right, so let's think about an example. How about this? S3. So here are the elements of S3. So I've got row 0, which is the identity. I have row 1. Oops, that's not a row. Hold on. Let me just put them all in. So let's say, and then row 2 is and then let's have mu1. So these are all the different ways we can shuffle things around. And that's all you can have, right? There's only 6 rearrangements of the numbers 1, 2, and 3, because you have 3 choices for what you can put in the first spot. But once you did that, then that one's stuck. So you've only got 2 choices for what to put in the second spot. And once you did that, then that one's stuck. And then you've got 1 choice for the last spot. So 3 times 2 is 6. Here they all are. And and actually, what is the multiplication table like? Well, you know, you can sort of go on and on about it, but I'm just going to pull it up because if it'll let me. You don't need to copy it down, it's in your book, but I do want to be able to sort of look at it together. This is what the multiplication table looks like. So for example, what happens if I do row 1 and then what if I do, I'm looking at this element of the table, which is row 1 time row 2 times row 1. In other words, do row 1 first. So who goes where? Do row 1 first. 1 goes to 2, and then 2 goes to 1. So we keep writing sigmas. So 1 goes to 2 and 2 goes to 1. Fine. Do row 1 first. So 2 goes to 3 and 3 goes to 2. Well, obviously this will be a 3, but let's just check. 3 goes to 1 and 1 goes to 3. So that's the identity. And oh, that's what we got, row 0 here. And you can do that with all of these and you get this multiplication table. Is this group abelian?
No, it's not symmetric on some of the mu's, looks like.
Yeah, that's right. Thanks, Hunter. It's not symmetric on some of the mu's. So let's just sort of pick a random one. So if I've got mu2 row 1, I haven't checked it, but is that the same thing as row 1 mu2? It's not. So no, not abelian. mu2 follows row 1 is mu3. Row 1 follows mu2 is mu1. Not the same. Okay, you might wonder, where do these crazy symbols, crazy names come from? Why did we call them this? Why not just call them element A, B, C, D, E, F or something like that? And there's good reason. So let's think of this new group. Was anyone have any questions about this S3? I don't, you don't have to multiply them all out yourself. It would be good to multiply one or two of them out to be sure you're comfortable with multiplying them out. And then you just can trust that, that the table's right. Okay, let's look at this other group called D3. Let's say this is the group of symmetries of an equilateral triangle. Let's try to figure out what all the symmetries are. What does it mean to be of a symmetry, for a shape to have a symmetry? That means it's a motion, but I can't just move it over somewhere else. I have to move it and have it land exactly where it was, but maybe the vertices are kind of moved around somehow. So for example, one of these could be do nothing. That's the boring symmetry. That's the identity symmetry. We called that row 0 above. What's another symmetry? What's another motion of this triangle that will bring it back to the same triangle, although maybe the labels will be moved around?
2 goes to 1 and 1 goes to 2.
2 goes to 1 and 1 goes to 2. Yeah, and so what could that look like? Well, that would be if we used, I wonder how many of these I need to draw. If I had, this was my original one, and I went to, what would the motion be?
It's like flipping it 180 degrees around a vertical axis.
Yeah, so exactly right. We're flipping it around this vertical axis. Okay, this one is mu3, I think. Let's see what it, so 1 and 2 get exchanged and 3 stays the same. And I think that's the same as our mu3 up here. Okay, it is. So mu is like an M. What do you think M for what? M's for mirror. So these are the mirror reflections about these different axes. So I don't need to have these anymore. So, you can do other ones of them. You could do like mu1 is mirror reflection across the axis that goes through 1. So 1 stays where it is and 2 and 3 get swapped. And so what does that look like? Well, 1 goes to 1, 2 goes to 3, and 3 goes to 2. And that's mu1. What do you think the row stands for? Row's an R. Let's look at this row 1. Row 1 sent 1 to 2, 2 to 3, and 3 to 1. What kind of action is that?
Rotating.
Yeah, it's rotation. It's rotation. So rho is for rotate. So that's rotating one third of the way around, rotate 2/3 of the way around. That's what these are. So this is a rotation. So one goes to two. Hold on, which way do I want to do this? So one moves to spot two, 2, 3. Okay, so actually, it turns out that the group of symmetries of an equilateral triangle is the same as S3. Even they're just sort of equal. Okay. Here's a question. What are the generators for this group? Let's look back at the table. Maybe the table will help us. You can either think in terms of the table or you can think in terms of the motions. Do I need to include the identity as a generator? No, in fact, I don't ever want to include the identity as a generator because any other generator to the 0 power is going to give the identity already, right? And then any power of the identity doesn't really get anywhere. So yeah, so we don't want to include the identity. What if we include one of the rotations? If we include row 1, how am I going to mark this? If we include row 1, then row 1 times row 1 is row 2. That's good. And row 1 times row 2 is row 0. And now I've got all the rows. So including row 1 gets all the rows. So, and the same thing would be true if we included just row 2. Row 2 would give me row 1 and row 0. So we need one of the rows. Who knows which one? So I could use one set is row 1. Then how many mu's do I need? Do I need all 3 of the mu's? I don't. You can see that pictorially, and I wish I could, maybe I can try to show you on my hands. So if the, I don't have anything triangle shaped, pretend this is triangle shaped. If this is the triangle and I want to flip, and let's say I only have the flip along this axis, and I wish I had this one, I could just rotate it like this and then do the flip. So if I have one flip, I can flip along this one and say I can rotate, flip, and then rotate back, and I've done the flip. We can see that here, if I have one of these flips, if I have like this one, well, then I can get mu2 out of it by one of the rows. And I get mu3 out of it by the other row. So once I have one of these, I get all the rest of the mu's as well. So it's one of these and one of these. I don't care which one you pick. But you need a rotation and a flip. And the best thing to do as an exercise at home, cut out an equilateral triangle out of paper. and label the three corners 1, 2, and 3. And just try to see, say you want to have something that corresponds to the flip across the vertical axis, pretend you only have one on a different diagonal axis, and see if you can figure out a way to rotate and flip and rotate to get the thing that you want. Given only one mirror reflection and all the rotations, convince yourself that you can achieve all the other reflections. There really is no substitute for building up your own intuition this way. And plus, it's kind of fun. Okay, what about D4? Example D4. Group of symmetries of square. So I wanted to, let me pull these down. I wanted to just have, oops. I wanted to have these just so I got the labels the same as in the book. It doesn't matter how you label them. There's no chosen from above way to label them. But if I didn't match the labels in the book, then you might get confused when you looked in the book later. So, well, what do we have? We have this square. What are the symmetries like? Well, row 0, that's going to be easy. That's the identity. That's do nothing. What else could we do?
You can flip it upside down. So 1 goes to 4 and 2 goes to 3.
Yeah, you can flip it upside down. So like here would be your mirror. I guess let me do a separate thing. So your mirror would be like this. And let's just call this, I don't care which mirror it is. Let's call this mirror 1. And if I wanted to write it as a permutation, 1 goes to 4, 2 goes to 3. What other ones do we have?
You can rotate it 3 times.
Yeah, you rotate it 3 times. So I could have row 1 is 1, 2, 3, 4. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. I can do that again. So if I rotate twice, and 1 goes to 2 goes to 3. So 1 goes to 3, 2 goes to 4, 3 goes to 1, 4 goes to 2. If I rotate 3 times, thanks. Should have thought of an organization of this before I really got started here, but this is what I did. If I rotate 3 times, then 1 goes all the way around to 4. Are there any other mirrors?
diagonal wise.
Yeah, there's diagonal ones. So there's diagonal ones, and then there's also another horizontal, I mean, another non-diagonal one, which would be vertical. So let's see, so the vertical ones are like, the other vertical one is so let's see what happened. 2 and 1 change places, and 3 and 4 change places. And let's see, so what did I just say? 2 and 1. And 3. And then, then there's the diagonal ones like Kelly was saying. So here they all are. The rows and the deltas are for diagonal. That shouldn't be a surprise. And then the mu's are for mirror, and the rows are for rotate. And here's the table for them. Do you notice anything about this table?
Isn't it a billion?
Is it a billion? Let's see. So if I do, let's just pick some random mu2 times row 3 and row 3 times mu2. Okay, already that one doesn't work. So it's not a billion. Some of it, there might be some symmetries in it, but maybe not overall. Tanner, you might have noticed a billion like right here. And that's because, what kind of subgroup is this? This is a subgroup. Can you see that? This is a cyclic subgroup. And that makes sense if you're going to take a square and you rotate it, and you rotate it again, and you rotate it again, and you rotate it again, you get back where you started, right? So the generator is rotate 1 time. The order of it is 4. So there's a cyclic subgroup there. And you know that cyclic groups are abelian. So maybe Tanner was seeing that this portion of it here is abelian. This sort of subgroup is abelian. In fact, it's a cyclic subgroup. There's other cyclic subgroups because of order 2. What would that be? Well, any of the mirrors, if you do the mirror and you do the mirror again, you get back where you started, right? So if I have any of the mu's, mu squared is the identity, and there's a very small cyclic subgroup. Any of the deltas, delta squared is the identity, there's a very small cyclic subgroup, order 2. Okay, so those are some of the properties. I want you to see one more. Oh, here's a question. Here's another question. Is this S3? 4. Is D4 the same as S4? D3 was the same as S3. We can see right now what all the permutations are in D4. Is there any other permutation that's not represented there? There has to be. How many possible permutations are there of 4 letters?
24.
24. Yeah, let's see, I've got 4 for the first position, and then 3, and then 2. So it's 24. I've only got 8 here. Wait, is it 24? 4 times? Yeah, that seems right. Okay. So it's definitely not the same. No, not enough. But in fact, D4 is a subgroup of S4. D4 is a group, S4 is a group. Everything in D4 is a permutation. So, okay. What's an example of something that's not in S4? Well, for example, if I look at this, this rectangle or square, and I only move these 3 around, but I left 4 alone, you can't do that and have it still stay a square, right? You have to sort of rip the square up to do it. So that's not a symmetry of a square, but it is a permutation. So this represents a permutation in S4 that's not a symmetry in D4. All right, so who's got questions about any of these things? I'm going to build on it in a second. It's about to get really heavy. So I want to be sure that we're all shored up before that. Okay, maybe we're good. All right, here's I want to look at this table again. Maybe I can erase these things. I hope I can. Still okay, good. Okay, so let's let's look carefully at the table. And this, it doesn't have to be a group of symmetries. It can be any group at all. Okay. But there's something I want you to notice about from tables. And we've kind of talked about it before, but we didn't really express it in this particular way. So what's true about every row, let's say? And same thing for every column. Every row has to have what? If it's a group.
One of
I'm
each
sorry.
of the elements.
One of each of the elements, that's right. Every element has to be represented exactly once. Nobody is doubled up, because if you double up, then left cancellation or whatever says that they're the same, and that's can't be in 2 different places. You can't double up. And then there's not room for, can't be any holes. So all of the group elements appears in every single row. For now, let's just think about this row, picked totally randomly. This row is a rearrangement of the original set. This row, let's all move together. This row represents the permutation. That looks like this. Well, let's see. Row 0 went to mu2, and row 1 went to delta 1, and row 2 went to mu2, and row 3 went to delta 2, and mu1 went to row 2. I wish I'd chosen a smaller table, and mu2 went to row 0, and delta 1 went to row 1, and delta 2 went to row 3. That's the permutation represented by that row. Oops. So each row in the table represents a permutation. Of the group. And so this was an example of a permutation associated to the row U2. Can you see that? Okay. How did we get this permutation? I mean, we read it off, in one sense, we just read it off the table without having to think. That's okay. But also, we know that in order to get from, like, in order to get right here, we took mu2 times rho 2. So what got rho 2 to mu2? Answer was, well, what is the answer? How did this permutation take rho 2 to mu2? What's the equation? What does it mean to be in that position of the table?
Is it just P2 star mu2?
It's yes, but the other way around, because the mu goes, the thing on the left goes before the thing on the top. Yeah, so it's going to be mu2 composed with rho 2 is rho 1 is mu1. Oh, what did I just do? I picked the wrong. Oh, I see. I wrote this wrong. That's what I did. That's not a 2. I just happened to pick the one that I wrote incorrectly. That's unfortunate. Okay. What about any of the other ones? How did I get from mu2 to rho 0? Mu2 to rho 0, I got there by multiplying on the left by mu2. So, you know, mu2 times rho 0 equal mu2 times mu2 is rho 0. I guess this is the orange, so maybe I should color code it. In fact, any of these happens by multiplying by mu2 on the left. That's how we got all these, right? Multiply by u2 on the left. This permutation came about by multiplying by mu2 on the left. Okay, every element of the group can be thought of as a permutation of the group. So the moral is this. Every element of the group can act as a permutation of that group. by left multiplication. This leads to something kind of amazing, which we're going to road to our building to. Okay, so let me just give you a definition so that we can build to it slowly. So this is, we're sort of defining what we sort of went through in detail above. I'm just giving a formal definition for it. And I'm just going to say it's the permutation associated to a group element. I'm defining how to do that. Here's how we do it. Let G be a group. And X and G. Then we define lambda sub X as a map from the group to itself as the permutation of the elements of G given by the X row of the table. In other words, or specifically, I need G and G. Where does G go under this permutation? Just like the above, where does row 2 go? To find out, I multiply on the left by mu2. Where does mu2 go? To find out, I multiply on the left by mu2. Where does G go? To find out, I multiply on the left by G. That's the definition. So I would call this, going back with that notation, I would say this is lambda sub mu2 applied to row 2. And this is lambda sub mu2 applied to mu2. Okay, so things are getting kind of meta, right? What we have is at the base level, we have a set of elements. And then maybe we have functions which are, I mean, this is possible. This is in the picture that we have now. That's the way it is. Functions are permutations of the element. And then that's a group. And then we can think of another group from that based on that group, you know, permutations of that other group. So, so you can get whole stacks of them. All right. So here's an exercise for the interested reader. Which is all of you. I hope it's all of you. Except for the interested reader, show that this is one-to-one and onto. So it actually is a permutation. We've just defined it, but you need to show that it's one-to-one and onto. So define lambda as above. So for show lambda is one-to-one and onto. This will be a good exercise. It'll bring together, it'll make sure you see which parts of having a group sort of come into play. And it'll also, frankly, just force you to get comfortable with the new notation and the new set of things. So I recommend it. Okay, what questions do you have about this so far? Does that mean it's good, or does that mean you're just shell shocked? Because it's about to get worse. I mean, it's about to get better. Come on. What am I saying? Okay, here we go. Here's Cayley's theorem. And that's really what we've been leading to. I took this group. Every element was a permutation, but that's just an accident. This could have been any old group that I wanted. This could have been the Clyde 4 group. This could have been Z6. Who knows? Could have been any group that I wanted. And I could have done the same thing, right? All I need is a group and a multiplication table to do this kind of activity. And if I do, each group element is a permutation. In fact, if I take the set of group elements, I can think of that as a set of permutations. It's better than that, because the set of group elements, which can be thought of as the set of permutations, is actually a group of permutations. And that's what Cayley's theorem says. So Cayley's theorem says that every group is isomorphic to a group of permutations. Every group is isomorphic to a group of permutations. Every single group is isomorphic to a group of permutations. So, at the beginning of this chapter, I put little stars all over it, saying that permutations are important. I mean, and this is a good reason why they're important, because every single group is one of these, right? You can describe everything in terms of permutations. So in some sense, you can feel like, wow, problem solved. On the other hand, permutations are super complicated. The subgroups of permutations are super complicated. So it's a nice characterization, but it doesn't necessarily make the world of things any smaller. Okay, so I want to talk about the proof of this. Okay, so what's all the setup? So let G be a group. We want to show that it's isomorphic to a subgroup, to a group of permutations. And in fact, we're going to show it's isomorphic to a subgroup of S sub G. Thanks. What do I mean by that? Take an element of a group. It can be thought of as a shuffling of the elements of the group, just like we saw. That row of the table is a shuffling. It's a permutation of the elements of G. So it's an element of S sub G. That we've all talked about. The only thing really that's missing is the group part of it, frankly. But that falls out pretty easily. Okay, so how can we do this? So we need to find a one-to-one homomorphism from G into SG. Let's call it phi. No, why not do it that way? one-to-one and homomorphism, why didn't I also say onto? That should be a capital G. Why didn't I also say onto?
Because it's a subgroup.
A subgroup, that's right. I'm not saying that's all of S sub G. I'm just saying it's a subgroup of S sub G. So it'll be mapped in there somehow. And it's gonna, so it'll be onto its image, onto whatever it maps, whatever it hits, right? That's gonna be the thing that the group that it's onto. Okay, here's how we're gonna define our function. Okay, so first of all, just like as we did above, so as above, so choose an X and X. Do you want me to go through this part again about getting the associated, oh, what just happened? Stop that. About getting the associated function, or do you feel comfortable with this? I can include it, re-include it in this proof if you want me to just talk through it again. Would you like me to talk through it again or no? Not, okay, yes, okay. So let's just start from the beginning here. So choose a fixed X and X. Not X, sorry, and G. For each little G and G, define lambda, how should I say this? I should really say, well, it's fine. Define lambda X of G to be X times G. Note that that means lambda X is a map from G to G. By your homework or by your exercise, this is 1-to-1 and onto. So it's permutation. That means lambda X is an element of S sub G. So I've just now defined how you can get from X, which is an element of G, to lambda X, which is an element of S sub G. That's what my phi is going to be. To do phi, I need to be able to get from elements of G to elements of S sub G. And I've just described that mechanism to do that. So here's how we're going to define phi. So now for every X and G, so that's for, yeah, now I'm defining it in general. Define phi, I guess, which goes from G to S of G by phi of X. What permutation does X go to? It goes to the lambda X permutation. What do we have to show? Who knows where we are in this proof?
I'm guessing the homomorphic part.
Yeah, right. We have to show the homomorphic part, and then it's 1-to-1. And then onto whatever it's onto, whatever it's onto. Okay, so so show homomorphism. Okay, so let's choose, suppose A and B are in G. such that, oh, sorry, not such that anything. I want to show that phi of A times B is phi of A times phi of B. So let's figure out what they both are. Phi of A times B. Well, here's our definition of phi right here. Phi of A times B is just lambda sub AB. And phi of A times phi of B is lambda sub A composed with lambda sub B. Yeah, these times are composed. I want to show these are the same function. Both of these are permutations. Want to show they are the same function. But we still have it in the chat what it means for how you show two functions are the same. Choose an arbitrary element and see that they do the same thing. So let's choose an arbitrary G and G. Then phi, let's just start with the lambda. Lambda sub AB of G, well, that's AB times G. That's just the definition. And then using associative law, and then that's lambda of A applied to BG. But BG is lambda B of G. So this is lambda A of lambda B of G. And this was phi of AB. Oops, not a comma. Okay, in just a few more seconds, since this is a whole lot of infrastructure to bring up, I'm just going to say something about the one-to-one. What do? Well, we suppose two elements of G such that phi of A equals phi of B. Want to show A is B. That's just what definition of one-to-one. Well, phi of A is equal to phi of B. That means that those functions are the same. So so let's apply them both to the identity. So phi A at E has to be the same thing as lambda A at B has to be the same as lambda B at E. That's just A times E. So A is B. Bam. Okay, so that was a little rushed at the end, but that's Cayley's theorem. And it's 3:50, so you can go now. But if you have questions, I've got office hours on the weekend, and we'll start up talking about Left-Burgular representations, which this is next time. All right, so okay, great. Have a good weekend. I'll see you later.
Thank you.
Bye.